one revolution around the Earth, which means the time period of Moon to complete one revolution around the Earth is 28 days. A circular orbit around any planet, then you can actually use this particular equation in order to find out what is the time period of that particular satellite. The total energy and kinetic energy have the same magnitude value, and potential energy will be double that of this particular kinetic energy. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were learning about gravitation. So what exactly is gravitation, how it functions, what is gravitational potential energy, and what is acceleration due to gravity? Everything was studied. Now we are going to look at some small terms and one very big important law. So time period. So what exactly is a time period? Time period is just the time interval when you need to complete something, right? For example, if this is the big planet we are in, that is Earth, then the moon takes around 27.3 days, 28 days to complete one revolution around the Earth, which means the time period of Moon to complete one revolution around the Earth is 28 days. Or for one other fun example, we can say that if Earth is rotating on its own axis, Earth takes 24 hours to complete one rotation. So we can say that the time period of Earth is 24 hours. Or again, if you want one more fun example, we can say that, okay, Earth revolves around the Sun and it takes 365 days. So we can say that the time period to complete one revolution around the Sun is actually 365 days. So again, you all know what is time period. I don't have to re-explain and give you examples about what is time period. So here we are going to learn about what is the time period of a satellite. So what is the time period of a satellite? It is the time taken by the satellite to complete one revolution around the Earth, and that is known as the time period of the satellite. For example, so we can actually calculate what is the time required by the Moon to complete one revolution around the Earth, and we can calculate, okay, what is the time required for that, how many days it will take, how many hours it will take, we can do that. That is simply known as the time period. So we are going to find out what is the time period of a satellite. So let's get right on to it. So we do know that time is nothing but distance divided by speed, right? Because again we know that speed or velocity is equal to displacement or distance by time. So from this relation I can say that time will be equal to distance by speed, right? It is that simple. If I want to find the time of something and if I know the distance and speed, I can easily calculate the time using this particular formula. Then again, in this particular case, I am going to calculate the time period. So I am going to indicate that using the capital letter T. Again, so in order to calculate the time period, that is capital letter T, I have to know what is the distance that particular satellite is covering. So assuming that it is covering a perfect circular shape, that is, I am assuming that, okay, it is almost covering a circular shape. Most of the times it is an elliptical shape, sometimes it is a circular shape. But for our ideal sakes, let's say that, okay, the satellite is going to cover a circular pattern around the Earth. So if that is the case, then I can say that, okay, the distance covered by the satellite, that is, the distance covered by the satellite from the starting position till the ending position, that is 360 degrees. It is the circumference of that particular circle, or simply it is nothing but 2 pi r, where r is the radius of that particular circle, divided by speed. Speed is retake. Here again we are expressing speed in terms of velocity, because again both are the same thing. Speed is just the magnitude, but we are taking velocity since it is a vector quantity and directions are very important and we are learning physics, so we are taking velocity. So 2 pi r by velocity. Here the velocity is nothing but v naught. That is, here the velocity is the orbital velocity of that particular satellite. So the distance will be 2 pi r and the velocity will be orbital velocity v naught. So how can you write it? So I can again write it as t is equal to 2 pi r divided by V naught is nothing but orbital velocity which is equal to root of gm by r. So I can write it as root of gm divided by r. Right. Now, this particular equation is what? I can take the r outside of this particular equation and drive it to the numerator. That is, this particular equation itself can be written as 2 pi r divided by root of gm divided by root of r. Right. Root gm by r is nothing but root gm divided by root r. So, this particular root r can be taken to the numerator. If I take it to the numerator, I can write it as t is equal to 2 pi r divided by root of gm into root r. Again, here we do know that root of something can be expressed as power of something. That is, if I have root 2 or in, let's say, root x, I can say that since this is the square root of that particular x, I can write it as x raised to 1 by 2. Right. If it is a square root, I can write it as x raised to 1 by 2. So, in that same logic, I am going to write this particular root r as 2 pi r into r raised to 1 by 2 divided by root of gm. Now, what is this r into r raised to 1 by 2? It is nothing but a raised to m into a raised to n, which is equal to a raised to m plus n. Again, this will become 2 pi r into r raised to 1 by 2, which is r raised to 1 plus 1 by 2. 1 plus 1 by 2 is nothing but 3 by 2. So, we can write it as, time period t is equal to 2 into pi into r raised to 1 plus 1 by 2, which is 3 by 2 divided by root gm, or simply 2 pi r raised to 3 by 2 divided by root gm. So, this is the final expression for the time period of a satellite. If you want to calculate the time period of any satellite which is having a circular orbit around any planet, then you can actually use this particular equation in order to find out what is the time period of that particular satellite. And again, time period of satellite is very simple, and again, if there is a satellite, if it has mass, if it is orbiting around a certain object, then obviously there will be energy for that particular satellite. So, let's see what is the energy of that particular satellite. So, again, what type of energies do you know? Again, it's very simple. If this is the planet, let's say it is Earth, and a satellite, let's say the moon is orbiting this particular satellite, then I can say that, okay, that is a mass. That is a mass that is moving. If a mass is moving, obviously it will have momentum and it will have kinetic energy. So, again, if this particular mass is moving around with a velocity v, then I can say that, okay, it has kinetic energy, it has potential energy also. So, there is a mechanical energy, or simply there is a total energy to that particular system, right. So, first I am going to calculate what is the kinetic energy of that particular system. So, kinetic energy Ke, again you can also indicate kinetic energy as T, but again in lower classes you don't generally do that. That is why I am just taking K dot E or Ke. Ke is equal to half mv square, but again here the v is the orbital velocity. Again, if you are taking the velocity of any satellite, it is just simply the orbital velocity which it is orbiting about. So, we can say that, okay, it is not v square, it is v naught square, and m is nothing but the mass of the satellite. So, I can say that, okay, this is equal to half m into root of gm divided by r whole square, right. So, I can write it as half into m into gm divided by r, or simply I can write it as g m divided by 2r. So, this will be the kinetic energy, right. There is nothing there, it is just a simple substitution in order to find what is kinetic energy. right? So this will be the kinetic energy of the satellite which is orbiting about a planet which is at a radius of r away from the planet, where m is the mass of the satellite and capital M is nothing but the mass of the planet. So this will be the relation, or this will be the equation in order to find kinetic energy. Now obviously if you are finding kinetic energy, we have to find potential energy also, which we have already found it out, right? We have already derived and found out what is the gravitational potential energy of anything. It is nothing but minus g/m by r. We have already found it, so we are just going to write it also. So again, we have already found out what potential energy U is. U is nothing but minus g/m divided by r. We did a long derivation and we found out what is the potential energy of any system or any mass which is at a particular distance. It is nothing but minus g/m divided by r. So we have the kinetic energy, we have the potential energy. Now we have to calculate what is the total energy of that particular system. So again, we do know that total energy TE is nothing but KE plus PE, or simply total energy is equal to kinetic energy plus potential energy. Again, don't get the misunderstanding that total energy is just kinetic and potential energy. Here we are only considering kinetic and potential energy. Total energy of a system is actually the culmination of all the different type of energies that system possesses. It can be gravitational potential energy, it can be kinetic energy, it can be vibrational energy, it can be thermal energy, it can be any other sort of attractive energies or repulsive energies it possesses. So total energy of a system is actually equal to the net energy that is contained in that particular system. But here I am only considering kinetic and potential energy because only that much is necessary for you, and this particular system we are just calculating what is the kinetic and potential energy because that much only is needed for our calculations. So again, this can be written down as g/m divided by 2r minus g/m divided by r, right? So what is so special about this particular equation? What is so special about this particular equation that it seems so similar? So it just so happens to be that these two equations are very similar to each other. So what is that similarity, what is that connection and all that, I'll tell you, but I hope you can figure out in the meantime. So again, here I can say that, okay, g/m by 2r minus g/m by r, how much it will be? How much will it be? If you have half of something and you subtract one more from that, you will get negative half only, right? So, or else I can simply say that I can take the g/m by r, that is the g/m by r outside of this particular bracket, then I can say that, okay, it is g/m divided by r into 1 by 2 minus 1, right? If I take g/m by r outside of here, then I will get 1. If I take g/m by r outside here, then I will get 1 by 2, right? Because there is a 1 by 2 here. So 1 by 2 minus 1 is simply minus 1 by 2, right? If you have half and you subtract 1 from that, you will get minus half. So you will get the total energy as, that is the total energy TE will be equal to minus g/m divided by 2r, right? So see, the important assumptions you have to understand here is that this is the kinetic energy, which is g/m by 2r. This is the total energy, which is g/m by 2r with the minus sign. So what is similar in between them? The similarity is that, okay, they are same in magnitude. That is the total energy of the system, the magnitude of the total energy of the system is equal to the magnitude of the kinetic energy possessed by that particular system. And then again, what is the relation between, what is the relation between potential energy and the total energy, or the potential energy and this particular kinetic energy? It just so happens that the half value of this particular potential energy is equal to the total energy of the system, or simply if I take the magnitude value, okay, I am taking the magnitude values for all the things, for potential energy, total energy and kinetic energy. If I take the magnitude values, then I can say that the total energy and kinetic energy have the same magnitude value, and potential energy will be double that of this particular kinetic energy. So that is the relation between potential energy, kinetic energy and total energy of a system. Just so you understand, these three equations are very simple and their comparison is also very simple. Modulus of U, that is modulus of or magnitude value of potential energy, will be equal to magnitude value of twice as kinetic energy, which is again equal to twice as total energy of the system, right? If I multiply 2 on both sides, all these quantities will be equal to each other. That is the simple relation or mathematical relation between all these three quantities. So I hope you understood that. Now we'll move on to one interesting topic, one interesting law I should have taken in the first term itself, but since it is so interesting, I kept it to the last. It is very simple. It is a small law found by a great scientist known as Kepler. So Kepler's law. Who is Kepler? Kepler is just an old scientist who found out that how planets actually move around our sun. So again, in earlier days, Copernicus and several other scientists propagated that, okay, Earth is not the center of the universe, Earth is not the center of our solar system. In fact, Earth is actually rotating around a bigger and massive body, that is the sun. But nobody believed them, and there was like struggles, there were suppressions and all that. All that is stories which we can say in our second PU, because actually it actually matters in the second PU. But again, for now, let's focus on Kepler. Then there was a scientist named Kepler. So Kepler actually figured out that, mathematically also, he figured out that, okay, planets are not revolving around the sun in a perfect circular pattern. So that is why when I discussed the orbitals or trajectories of satellite, I said it is not a perfect circle. It was not actually Kepler who said this, but it was Kepler who actually proved this and united all these laws. So that is why we call it as Kepler's laws. But anyways, he said that if this is the sun, the Earth is not rotating like this. For example, any planet, if it is near the sun, this is not the revolutionary path or trajectory of that particular planet. It is not a circular pattern. In fact, it is not even an enlarged circle. It is one other kind of form or mathematical form. It is known as an ellipse. You have already studied what is an ellipse in your first PUC mathematics, so I don't have to explain what is an ellipse, what is semi-major axis, what is semi-minor axis, right? I don't have to explain that. This is an ellipse, and we can take dissections like this, and each side will be A, and this will be the same. This will be the major axis, and this will be the semi-major axis, each of having A length, right? And the major axis will have together 2A. I don't have to explain any of that because you have already studied and you know that there are two focuses, one here, one here. So we have F2 and F1. So it has multiple focuses, or simply it has two foci, right? I don't have to explain any of this because you already know what is an ellipse. So again, what Kepler discovered was that if there is a sun, the planets will not rotate around the sun or will not revolve around the sun in a perfectly circular pattern, but rather he found out that planets actually revolve around the sun in an elliptical orbit with sun at one of its foci. That is, if this is a planet, let's say Earth is the planet, it is revolving around the sun in an elliptical pattern. So this is an ellipse. Assume that it is an ellipse. So in an elliptical pattern with sun at one of its focus. So if this is focus number 1, then I can say that, okay, sun is here. But for an ellipse, there is two focuses or simply two foci. So I can say that there is two focuses and the sun will be at one of its focuses and the planet will be revolving around the sun in an elliptical pattern. So obviously sun is a huge massive body, which means that there will be more gravitational pull on this side and there will be least amount of gravitational pull on the opposite side. So Kepler found this particular law first and named it as first law. So the first law, or simply known as the law of orbits, states that every planet in the solar system, or simply all planets, revolve around the sun in an elliptical pattern. That is first law, which states that okay, the orbit of any planet around the sun is not circular in nature, but rather it is an ellipse. So that is known as law of orbits, or simply first law of Kepler's motion. Now there is one more law that is known as second law of planetary motion, or simply Kepler's second law of planetary motion. So what the second law states is that the second law is about the law of areas. Again, this is all really mathematical based. So we have to talk about areas. What is the shape? Is it an ellipse? Is it a parabola and all that? We have to discuss that. So the first law stated that okay, planets revolve around the sun in an elliptical pattern with sun at one of its foci. Now we are learning that okay, there is something related to area in this particular figure, or when the planet is moving around in an elliptical path, there is some relation between the areas swept by that particular planet. So that particular relation is that if the planet is moving around in an elliptical path, then let's say that okay, this is the sun, okay, and don't worry about what is a perihelion. Is just the spot which is closer to the sun here, this part of the ellipse, and aphelion is nothing but the farther away point from this particular sun. Just remember it like that. You don't have to worry about what is perihelion and what is aphelion. So again, the important thing is that when Kepler observed or did calculations, he observed that okay, when the planet is moving around this particular elliptical path, it just so happens that the planet moves faster near the sun. That is, here it moves faster and here it moves slower. So here the planet actually moved slower and here it tried to move faster. So why did this happen? Obviously it is because the sun is placed more closer to this particular side. So again, so what did he learn? He learned that okay, since the planet is moving much more slower here and the planet is moving much more faster here, there is actually a mathematical relation because this is an ellipse. So he actually joined a line from the sun to the planet. Okay, let's say the planet was first in the position A, and after let's say delta t time, or after some time, after delta t time, the planet was in position B, which means let's say in 10 seconds the planet was in position B, or 10 days or 10 years, whatever you want to take. In delta t time, the planet was in B, position B. Okay, then he measured that okay, this will be the area. He drew two lines from the sun to the point first the planet was in, and then after delta t time where the planet is, he connected that line also, and he got a particular area here. Okay, he recorded that area as let's say delta A. Delta A was the area covered by the planet in delta t time on this side of the ellipse. Okay, then again he measured 2 points near to the sun. First he measured 2 points far away from the sun. Now he measured 2 points near to the sun. Let's say point C and D. So now he did that. Okay, the same delta time he took. The planet was here. He started measuring. Okay, the planet has reached this particular position. Okay, I measured for delta time on the other side. So I am going to measure the delta time here again. Where will the planet be? So surprisingly, the planet was moving faster now since it is near to the sun. So it moved to position D. So again in delta time, since it reached position D, he connected lines again and he measured the area. So he found out that in fact these two particular areas were exactly the same. So in delta t time, whatever area was covered on this particular side, the same area was covered here. So using that particular relation, he found out that okay, planets are moving slower in this particular side and it is moving much faster near to the sun. That is, in this particular side, the planets are moving really faster. So he mathematically drew this up and he named it as, okay, the law of areas. So to put it simply, he considered one area near the sun. He measured, okay, in delta t time, the planet covers this much area, okay, and then he measured one other point where the planet will be far away from the sun, okay, and then again in delta t time he measured what is the area being covered. Then he found out that both these areas were equal to each other. So he mathematically proved that and he stated it as a law. So the law stated that a line joining the sun to any planet, a line joining the sun to any planet sweeps out equal areas in equal intervals of time. That is, if that is the same thing I mentioned earlier, that is, these two areas will be equal to each other. He just put it mathematically. Or another way of the physical significance is that the planets move faster near the sun and they move slower away from the sun. That's why some nights are longer and some days are very short. So again, this is the law of areas, and that is the second law. The first law is that the planets follow an elliptical pattern, and the second law is that the planet sweeps out equal areas in equal intervals of time. Okay. And the third law is very complicated because it states t square is directly proportional to a cube. That is the third law. Or simply we can say that the third and final law states that the law of periods states that the square of time period of any planet is directly proportional to the a cube. A is nothing but the length of the semi-major axis. So it is directly proportional to the cube of the semi-major axis. Again, if you don't remember what an ellipse is, this is an ellipse. We can take sections of this particular ellipse. Then I can say that this will be the major axis. Now it is cut into two parts. Then we can call it as semi-major axis, and then each part of the semi-major axis is measured as A. So again, if I measure the time period of any planet, the square of that time period will be proportional to the cube of the semi-major axis. That is one particular relation that Kepler observed, and he noted it down, and that is known as the third law of Kepler's planetary motion, simply, or also known as the law of periods. So this is third law, which is known as law of periods. So the time period, so square of the time period is directly proportional to the cube of the semi-major axis. So that is all about Kepler's first, second and third law. So I hope you have understood everything about what is energy of a satellite, what is the time period of a satellite, what is Kepler's first, second and third law. So I guess I will see you all in the next session with a new chapter, because this chapter is over. Thank you.